Building the neural network is a what I'm in charge, but running it is a daily battle of unit economics. As generative artificial intelligence takes over the tech industry, organizations are realizing that the cost to train these systems is only the tip of the iceberg.
Training AI models, particularly large language models, can cost millions of dollars in computing processing time, but as expensive as training an AI model can be, it is dwarfed by the expense of inferencing. Each time someone runs an AI model, there's a cost in kilowatt hours, a cost in dollars, a cost in carbon emissions.
While pre-training demands massive upfront capital, the real financial drain happens slowly, second by second, with every user query. In the technology business, raw computational power is quickly shifting from a one-time capital expense to a continuous variable cost.
What is beautiful there, this is the game of real business. Because again, training is a fixed cost, but inference is a unit economics.
Building the neural network is a what I'm in charge, but running it is a daily battle of unit economics that determines survival. Engineering teams are beginning to look beyond the initial setup of large language models to focus heavily on daily operational metrics.
I think we've always
Managing throughput and latency is the invisible engine of the AI economy, dictating whether an app is responsive or unusable. Standard deep learning frameworks are highly reliant on GPU compute, making optimizations at the hardware level incredibly critical.
Has been a key reason why model inference costs have gone down so much. He was super involved in safe-based model work via his work at Mamba, the alternative architectures to transformers. He's the chief scientist at Together, and his work's been so impactful that SemiAnalysis basically noted that a huge part of the NVIDIA moat is the fact that Tree's doing all this work in the NVIDIA ecosystem.
To drive down the massive expenses of model execution, developers are forced to innovate at the lowest layers of software. Many software projects start by using third-party APIs to quickly test user interest and find product-market fit.
So cost is an issue, especially with scale. And I think that's kind of like where we started out. We start off with some of these kind of like foundational APIs as a way to figure out, is this a product that's useful? Does this help our ranking signals? Do our users like this? And then once we actually started getting that, both the cost of running that and how much we could run this on really becomes a bottleneck. So if you think about like summarization systems,
relying on hosted web APIs is a great shortcut for testing, but that strategy quickly becomes a financial trap at scale. The physical footprint of modern machine learning extends far beyond hardware, purchasing costs, and clean server facilities.
Each time someone runs an AI model, there's a cost in kilowatt hours, a cost in dollars, a cost in carbon emissions. On average, something like about 90% of an AI model's life is spent in inferencing mode. And therefore, most of the AI's carbon footprint comes from serving models to the world, not in training them.
A staggering 90% of a model's lifetime energy is burned during daily execution, not during training. Standard pre-trained models operate with a strict informational limit, possessing zero awareness of real-time events or private enterprise data.
There's a fundamental truth about LLMs, large language models. They are frozen in time. They know everything about our world up until their training cutoff date, and absolutely nothing about what happened 5 minutes ago, nor do they know anything about your private data, your internal wikis, your proprietary code base.
A static model is functionally blind to current events, requiring continuous context updates to remain valuable. As massive corporate clusters finish their initial training cycles, their physical processing power is repurposed for model serving.
And new capacity being added. The way I'm reading it is all of this will become inference compute. The cluster are being built for training, but 6 months later, the cluster will be used entirely for inference. We're seeing the paradigm shift from building vertical system. For example, OpenAI, there's inference engine for Sora. There's another inference engine for new version of Sora. We're building one inference engine for all the current and future model, for all the current and future hardware.
The physical architecture built for massive training runs is ultimately destined to spend its life serving queries. To understand how developers can optimize their serving platforms, we must look at what happens when a system processes a query.
Prompt caching, you need to understand what happens when we take a large language model, an LLM, and we send to that large language model a prompt.
The simple act of sending a prompt triggers a cascade of heavy calculations that define the ultimate cost of AI. Hardware manufacturers are rolling out specialized systems to manage the intense thermal and electrical demands of model serving.
We are announcing two solutions for AI inferencing in data center. These are two generations of products, the AI 200 and AI 250 family of products. The first one, AI 200, it's a rack level solution that scales down all the way from rack to cards to servers. And this rack level solution, it's direct liquid cooled.
As models grow, directly liquid cool rack solutions are transitioning from a luxury to a baseline physical requirement. Innovative software frameworks are emerging to optimize how language engines utilize scarce memory resources during execution.
Why VLM matters. It dramatically optimizes inference performance, speeding up responses, managing memory efficiently, and significantly reducing your infrastructure costs. At VLM's heart lies three critical innovations: page detention, continuous batching, and prefix caching. Page detention cleverly manages short-term memory, or KV cache as we.
Innovations like continuous batching and page-based memory management are essential to driving down the cost of each token. Traditional companies face an acute shortage of specialized systems talent, leaving general engineering teams to build complex platforms.
Again, one of the problems we have seen since Gen AI is that you don't have all the resources, you don't have all the AI engineers available. Some of these engineering leaders, like myself, we are in positions where we're asked to do AI without the AI resources available. And with no previous team or experience building AI. So learning was number one.
Companies are being pushed to deploy advanced language systems without the deep infrastructure experience typically required. To bypass massive central data centers, some developers are looking toward distributed computing networks built on consumer hardware.
The opportunity to solve the infrastructural challenge of AI, and by doing that through pretty much the deep-in approach, where we use the consumer hardware that's already out there to build a peer-to-peer network that combines the capabilities of small specialized AI models.
Decentralized networks offer a creative way to scale compute by stitching together thousands of smaller consumer machines. The rapid growth of generative algorithms has dramatically shifted what researchers consider to be state-of-the-art.
When I started back in 2014 or so, we were barely able to model NIST images, and it was all very blurry, and that was already a big result. And now, the bar has shifted a little bit in terms of what these models can do. So it's been exciting, and more specifically, my lab at Stanford has always been at the forefront of what these models can do, and always been innovative.
A decade ago, modeling simple images was a breakthrough. Today, models process complex language at extreme scale. The financial investments required to build out global artificial intelligence infrastructure are difficult to comprehend.
Today's number is $400 billion. That's how much money just the four hyperscalers, Microsoft, Amazon, Meta, and Alphabet, are spending or expected to spend in this year alone. For context, that's more than 15 times the Manhattan Project, 2 times the amount of money it took for us to do Apollo program, which literally put the man on the moon. And that number could globally reach $3 trillion.
Hyperscaler spending is surpassing historic projects like the Apollo program, highlighting the scale of this technological shift. Silicon designers are building custom microchips dedicated solely to running model inference as efficiently as possible.
Look, Positron AI is really, really focused in the world of silicon. So we are designing and building silicon for inference applications. And like, if you're following the news, if you've not been under a rock and have been seeing, inference is where all the spend is going and kind of where all the applications are growing, whether that's code generation on the enterprise side. Obviously, world building models and video models have really come up and shot to.
With the massive growth of video and generative code applications, general-purpose processors are being replaced by custom silicon. Open source initiatives are focusing on orchestrating distributed deployments on top of standard container platforms.
Today, we will look at the gaps and the promising open source approach LLMD provide. LLMD is a new open source project for the high performance distributed inference on Kubernetes. It can provide the little path for anyone to serve large generative AI model at scale with the fastest time to value and competitive performance.
Standardizing on open orchestration frameworks like Kubernetes is key to driving down infrastructure costs for developers. Developers are applying local statistical models to predict how neural networks react to changes in their prompt inputs.
And this model is post hoc, which essentially means that we only have access to the input and output, call that X and Y. And by changing X, we're going to observe how Y changes. And using this method, we can fit a linear model. In this case, we're going to use regression.
Treating model inputs as variables allows teams to build highly effective predictors of cost and accuracy. The transition from simple pattern matching to advanced, multi-step reasoning has occurred faster than almost anyone predicted.
In an era right now where even 6 months ago, if you'd have told me about the models we have right now, I wouldn't have believed you. The models have gone from GPT, generative pre-training, to reasoning models, and so much so now that we don't even call today's models LLMs anymore.
The rapid rise of reasoning models has completely changed the operational constraints of hosting large systems. Speculative decoding utilizes a smaller neural network to generate potential responses before confirming them with a larger model.
This approach follows the slogan draft and verify by using a smaller draft model to speculate about future tokens while a larger target model verifies them in parallel. This approach can generate 2 to 4 tokens in the same amount of time it would take a normal LLM to generate just one. Think of a writer and an editor.
Using a fast, lightweight draft model for simple words saves massive amounts of expensive GPU execution cycles. The ultimate commercial viability of any AI system is determined by the sheer volume of daily user queries it must serve.
First of all, there's just the sheer scale, the scale of operations. While training happens just once, inferencing happens millions or even billions of times over a model's lifetime. A chatbot might field millions of queries every day, each requiring a separate inference. Second, there's the need for speed.
While pre-training is a massive milestone, the real challenge is surviving the relentless demand of millions of daily requests. The distribution of capital inside machine learning projects is undergoing a massive, long-term shift.
And 8 years ago with machine learning, where there was most of the investment was in training, it was 80-20, and then when it went to essentially 20-80 within a couple years.
The industry is rapidly shifting its budget from upfront training to the reality of active model execution. User engagement is highly sensitive to model response times, making speed the primary driver of application success.
Second is the latency expressed in second per token, so how many seconds it takes to output the next token. This drives how fast or how snappy your application will look. So in ChatGPT, it's pretty fast. And the smaller model, the easier it is to get this really, really quick. So we want to minimize this for user experience. A good threshold to keep in mind is 250 words per minute, I think, is the average reader speed.
Matching the natural reading speed of a human is the golden threshold for real-world application design. The dominant market leaders in hardware have secured their position not just through silicon design, but through developer ecosystems.
I spent a fair amount of time thinking about the chips. I think certainly there's lots of competitors are trying to enter this space. I mean, AMD has been here for a while. Obviously, NVIDIA is dominant for a couple of reasons. They design very good chips, and they build very good software, and that creates this ecosystem where people build on that.
Building great hardware is only half the battle. The real mode is the software ecosystem built around it. Instead of focusing purely on resource cost, engineering teams must evaluate where their models can physically execute.
The process we generally think about is less around just the dollar cost, more on kind of like, where can I run this? And for us, the golden threshold has been, can we make this model run on a single A10 GPU or on any type of CPU requirement?
The ability to host a model on a single mid-range GPU changes the entire financial math of serving AI. Some engineering teams are choosing to bypass the entire database search stack by feeding all document data directly into the model context.
All of our documentation into the model's context window. Do we really need the overhead of embedding models and vector data stores? Is RAG becoming an unnecessary complexity layer? Well, if we accept that we can fit whatever data we need into the context window, then the argument for doing so basically boils down to one word.
While a massive context window offers complete simplicity, it demands serious raw computing power to process. The physical procurement of advanced silicon remains one of the largest capital outlays in corporate history.
So this is the most expensive part of AI right now. The chip itself just cost a significant amount of capital to procure. But then if you think about the whole process, in order to produce these models, we have to build the data centers and then build the training cluster. And then from the training cluster, you produce a model. But at that point, there's no value created.
Building clusters and training models is just prep work. Real value is only realized when users start calling the system. Smart serving systems recognize identical document inputs across conversations, retrieving previous calculations from cache.
Prompt caching, that processing work is getting saved. Now, later on in a new conversation or an API call, you could send that same 50-page document, followed this time by, instead of asking to summarize, we just provide some kind of different question. And the system will recognize that document prefix. It will retrieve the cached KV pairs.
Saving and reusing prompt context dramatically reduces latency and hardware utilization. Specialized serving tools allow teams to host open models with extreme throughput and minimum resource waste.
Faster response times, higher token throughput, and more efficient GPU utilization. Hopefully you get the theme. VLM consistently achieves state-of-the-art serving performance, providing up to 24 times higher throughput than standard transformer implementations, a huge leap forward for real-world workloads. It supports cutting-edge model optimizations like quantization of weights, activations, and even KV cache.
Achieving up to 24 times standard throughput represents a massive leap forward for production scale AI. The final physical limit of model serving is determined not by compute speed, but by the physical boundaries of memory and storage.
Memory and the performance of storage, even flash storage, even NVMe.
Computing fast means nothing if your processing units are sitting idle, waiting for data to arrive from storage. The transition from simple text generation to advanced system-level reasoning represents a fundamental shift in how we build software.